Okay. All right. So anyway, here's the problem. So as we get into chapter 7, what chapter 7 is applications of using the integral. And so one of the things that can be very common in these problems is using an integral. Now, it's a lot easier than chapter 4. Okay, you got to have the right mindset. When in chapter 4 we did all those derivative stuff, related rates, max min problems. Setting those up. There are a lot of different ways to strategies to use and types of problems, and we had some difficulty with some of those sections. And I think those things are harder. The integral stuff is generally easier. There's not that many options of what to do, and if you kind of look at the units, you can usually tell if an integral needs to be involved, and then you just have to decide. Okay, are we talking about net versus like total distance, or whatever the case may be. But if you think about units, it can really help you in knowing what to do, because the other part of the the derivative stuff in chapter 4 is we had to set up those functions, we had to set up those equations, then do the derivative and do all that stuff. Well, here, a lot of times the equations are given to us a lot more readily. We don't have to come up with them on our own. And then when we set up the integral, we get to use our calculator 90% of the time to just type in the integral. So let's take a look at this particular problem. So it says it's estimated that our current rate of consumption, C sub 0 gallons per year. Now it's important to understand that that's gallons per year, that's C sub 0, okay? So we're going to pay attention to those units. The oil supply of the earth will last 200 years. However, the rate of consumption, C, again, C is a rate here. It's kind of unfortunate they use capital C as a rate. If capital C is gallons per year, then what would be gallons? Well, big C, great big C, right? I mean, so it's, yeah, C, yeah, something. But anyway, understand that C is a rate. C is gallons per year. All right. So C is increasing at the rate of 5% per year, which would be this. Now, hopefully you recognize this. This is a special differential equation. Isn't this y prime equals ky right here? It's C prime equals k times C. It's that one we've memorized. So when we go to part B, they say show that this is the solution by solving this differential equation. Now, we haven't learned how to do that. We just memorized that was the solution. We knew it was a e to the kt. Well, here's our a, our initial amount. Well, that's our initial c is c sub 0. Okay, so we can tell that is a solution. So we'll just skip part B because we haven't learned that yet. We're going to learn in section 4, I think, of chapter 7. We're going to learn how to solve this differential equation and come up with this. So we'll get to that point, but right now we don't know how. So we'll just assume, hey, this is our C equation. And what does C stand for again? Gallons per year, the rate of consumption at any given year. Okay, but it's changing. It's changing. Now, part A, it says, in terms of C sub 0, how many gallons of oil are currently available? Now, remember what they said back here. If we were to keep at this rate, our oil supply will last 200 years. Right? Now, we're not going to. The rate of consumption is going to increase. But if we did continue with our current rate of consumption, C sub 0, our oil would last 200 years. So how many gallons do we have? No, it actually is not an integral of what, though? No. You see, because this is if the rate is changing. This is what's going to happen in the future. This is saying that if we continued at our current rate, the oil will last 200 years. So the rate's not going to, under that assumption, the rate's not going to change. It's going to stay C sub 0. And if it does, we'll have 200 years worth of oil. So how do we find the gallons for that? Wouldn't it just be C sub 0 times 200? Now, you actually could do an integral. You could do an integral of the gallons per year because we want to get gallons, right? So I want to take what Ali said. You actually could do it. 0 to 200. What would be the gallons per year that we would put in here? C sub 0. dt, right? The gallons per year would stay constant. It would just be this. Well, what's the antiderivative of C sub 0 with respect to t? No. So this is just a number. This is just a constant. So what's the antiderivative of like 7 with respect to t? 7t, right? So what would be the antiderivative of c sub 0? C sub 0 t at right bracket 0 to 200, right? So then we put in a 200 for t, put in a 0 for t, and what would we get? 200 times c sub 0. In other words, think of it this way, I think this is what Ryan was probably doing, is just saying, well, if we have, let's put a number, let's say we had 10 gallons per year is what we were using. We're using 10 gallons per year. That's going to last for 200 years. How many gallons do we have? 2,000, right? If we have 10 gallons per year we're using, and we're going to last for 200 years, we got to have 2,000 gallons. 200 times 10, right? So it's 200 times c sub 0. So you wouldn't have to do it as an integral, although by thinking of it as an integral, that's going to help us later. We'll get to that in a minute. But there's our answer to part A. There's this many gallons of oil right now. Okay, so now, our rate of consumption is not going to stay constant, however. It's going to change. And so therefore, our rate of consumption is going to be this right here. So what are the units on this right here again now in part B? The C equation, what are the units? Gallons per year. All right, now it says if we don't discover any additional oil, so in other words, we have this many gallons, that's all we got. If we don't discover any more oil, how long will it actually last? Well, we can kind of do what Allie just suggested we did a minute ago. The integral from 0 to what? 0 to something we don't know, right? T. Now, I wouldn't use T because we're going to have T in our equation here. So we could use T, or we use X, whatever. We'd have to change our equation. And then what's going to go in here? This equation, right? Because remember, this is gallons per year. This is the gallons per year we're consuming, right? This is the gallons per year we're consuming. And so how many gallons will we consume, okay? So we want to know how long it lasts. So what do we do with that? We got to set it equal to something because we got to solve for this x. What do we set it equal to? We'd set it equal to that, how many gallons we have, right? On this side, this is, think about that, inside that integral is gallons per year. When we do the integral, that's gallons. So this is how many gallons we're going to consume. So we want to know at what value x we will consume all of our oil, which is this number of gallons, right? Okay, now we can type that in our calculator. Now what about that c sub 0? That's just a constant. Could we pull that out? And then what can we do with it? Cancel it? So actually we could cancel out the c sub 0. So there you go. Now do that as a solve on your calculator now. Now on the actual, while you guys are typing that in, on the actual AP test, this would be perfectly legal. You could set up this, you would have to set up this equation. Any equation you're going to solve on your calculator, you have to have written on your paper. So you write out this equation. Now you can go to solve it, and you can just write down then your answer. Let's see if you can get that figured out, how to solve that. So we're actually going to solve this equation that has an integral in it. But again, your thought process would have been, I know this equation is gallons per year. I want to get gallons. Yeah, a lot of times we think antiderivative, but like we talked about yesterday, think integral. Set up an integral. This is the integral of the gallons used from year 0 to year x. What do you get? It says round to the nearest year. So that'd be 48 years. So interesting. So that oil would have lasted 200 years, but since our consumption is going up 5% every year, it actually lasts 48 years. Okay? All right. And so that was a tough problem because of that C sub 0. That gets confusing with the units, whatever. I just know people really get stuck on part A there. I mean, it's not a hard concept. Once you see it, you're like, oh, yeah, that's how many gallons it would be. But people just get stuck on that. And of course, if you can't do that, then you can't set up part C at all. So that usually is kind of a tricky one. All right, let's go on to number 4. I had kind of helped you, and I'd helped some people I know on number 4. We're going to come back and talk about number 4 a little bit, later because it does fit right in with what we're learning now. Now, we're going to skip part A, B, and C, and I know I helped talk with some of you about that, and I know you've already got it here. What did you get for A? What did you come up with for A there? Maybe it was the other class it was. I can't imagine the other class would be better than you guys. What did you get for A? 1/2. Okay, so this point is 1/2. And then what do we get for that y value? Probably doesn't matter. 1/2 squared would be 1/4 minus 3. What's that? -2 3/4. I guess is what that would be. And then this point right here is, what was that point? 7/2, 3.5. And then that'd be 3.5 minus 3.5 squared. That's a 4. Okay, so that would be those 2 points right there. And of course, we got the point 2, 1 right there. Okay, all right. And down in part D, this is the part we're going to be working with today. Find the integral that gives you the area of region R, which is this region right in here. That region right there, we need to find the area. Now, some of you, I know there was a few people were talking yesterday, well, right at the end of the period, we were talking, well, you can find the area of the parabola, which is this little piece, and this area over here, and then you got kind of a triangle in here, and then you got some, whatever. Okay? And you could maybe come up with it, but here's the first question we have to ask ourselves. Does it matter that part of this region is below the x-axis and part of it is not? Now, Ryan says no. Anybody else have a thought on that? Now, I understand if you're saying, I don't know, you haven't told us. Well, how would I know? How would I know whether it matters or not, right? What they ask for is they want the area of this blue region. So to you, does that make sense that that area would be negative because more of it's below than above or whatever? Okay, well, good. If you're saying no, then that's right. When we're talking about the area between curves, between functions, the area of a region, that's different than saying the area under a curve. When we talk about area under a curve, we're talking about the area from the curve to the x-axis. And that could be positive or it could be negative, depending if it's above or below. But when we're talking about just this given region, what's its area? We want that to always be a positive number, just like in geometry. Area was always positive. We want that to always be positive. Now, I've made a little picture here that I hope kind of helps make sense of that. Okay, let's see. Okay, so when we do area under a curve, several different things I want to talk about today here. When we do area under a curve, remember it came from this integral sigma idea where we add up a bunch of rectangles, right? So if I've got this curve and we're going to do this area right here, I'm just going to add up a bunch of these rectangles. Now, how do we do that? Well, we do the length of the rectangle times the width of the rectangle. Well, the width, that is the delta x, okay? The length of the rectangle is this function value. Well, if the function is above the x-axis, then this is a positive value. So we have positive length times positive width, that's a positive area. But over here, what's this function value? What's that function value? Positive or negative? This function value right here? Just this function value, that's this y value right here is negative, right? This y value is negative. Okay? Kelsey's not here, so some of you are going to have to answer. Besides her, okay? This function value is negative, right? So when we do this, right? When we do this sigma right here, that's going to be a negative value, right? F of whatever, that's going to be negative. And then our width, that's always positive, right? We just defined it that way always. Our width is always positive, okay? And so, therefore, negative times positive, right? Now, you're right, width could become negative if you're going backwards. I think that's what you're saying. If we do the integral from b to a and we go backwards, yeah, that's when our width becomes negative, and then that's why everything was always opposite. Because then we would have a negative y value times a negative width, because we're going backwards, and then that's why that would end up being a positive area. Okay, so we got into that thing with negative and positive when we were doing the area under a curve, which meant from the curve to the x-axis. Okay, but we're going to be doing something different than that when we talk about this area here. So let's just look at this blue area right here, and we're going to do this problem. You don't need to draw it out yet, but we will in a little bit. So let's say we're talking about this blue area. Now, I was able to do this earlier, last period. Let's see if I can do it this period. The Okay, so if I take, dang it. Try that again. What am I doing? Oh, man. Oh, golly sakes, that really screwed this up. All right, let's try this. You okay? I know, that's why I'm asking. I mean, you're good? All right, all right. Because calculus, hard to do calculus on an empty tank, you know, I don't know. All right. That's pretty cool. But does that blue area change? The blue area, the blue region does not change. We're talking about, Carly, is that area between curves, when we're doing area between curves, okay? It doesn't change. As I move those curves around, it doesn't change. Now, think about, oh, shoot. There we go. All right. Think about if we were just going to do, let me do, hang on here a second. Let's say we were just going to talk about this area, the area under the cube root graph, which is, now I'm not going to be able to do this one. This one's not going to work to do what I just did. But let's say, forget the parabola, the x squared. Let's just take the cube root graph here. Okay, this is a cube root graph. Let's say we picked the cube root graph up and started moving it around. Would that blue area change? Then that blue area would change, right? Because it's with relation to the x-axis. So now when we move that around, that changes. So the negative, the positive, that all matters. But if we're just doing the area between the two curves, then where the x-axis is in there has no significance whatsoever. There is no such thing as positive and negative area. It's just positive area. Okay, now, how are we going to calculate that? Well, again, we're going to come back to this. We're going to come back to this idea of what is an integral. An integral is like a sigma. An integral is an adding up of the thing that's in here. Now, f of x dx is like a rectangle, length times width. Now, I used to say height times width all the time, but you'll see why today I'm going to use length more than I am height. But length times width, length times width, length times width. Now, the length of our rectangle is the function value, and the width is the delta x. All right, well, now, to be able to do a rectangle, it would look more like this. Let's say we were going to do a left rectangle. Let's say we were going to divide this. Where does this intersect, by the way? Where's cube root of x and x squared intersect? 1, 1, right? So let's say we were going to divide this into 5 left rectangles, which on your homework you actually get to do a little bit of. Sorry, we're not being totally correct. Okay? Well, we were going to divide this, so each of these would be how what? 2/10, 1/5, 0.2, whatever. Okay? So our first left rectangle, of course, would just be here. There'd be nothing because it's right there. But our second left rectangle would actually look like this. You see how that would be the left rectangle right there? The left rectangle would actually be up off of the x-axis. It would hit the top curve there, and it would hit the bottom curve there, and it would be 0.2y, and there it would be. And the second one would be here down to here, right? And the left, there would be 2 of your left rectangles right there. And so doesn't it make sense that eventually if we had an infinite number of rectangles that we could just think of it as a bunch of rectangles added up here to get this area, right? Does that make sense? So what would the integral look like then to make that happen? Well, the integral would have to go from 0 to 1, because the rectangles would go from 0 to 1, right? So we'd have to know that intersection point. Now, what would be, think back to this, what would be the width of my rectangles? Well, that's the dx part, right? That's the delta x. Now, in this case, it'd be 0.2 if I was doing 5 of them. But let's say we're doing an infinite number of them, right? If we're doing an infinite number, then we got our integral, okay? Now, what is the length of my rectangle, which back here was just the function value, because it went from the x-axis. So whatever the y value was, that was my length. What's the length of this rectangle? The difference between the two y values, right? Well, now, let's talk about that a minute. What is this y value right here? Now, forget the 0.2 for a minute. Forget that we've divided that into 5. Just what is a generic coordinate of this point right here? X, comma. Now, we could do x, comma, y. Let's do that. Then what would be the generic coordinate of that point? Could I do x comma y there? I can't do that because why? The x's are both the same, right? But the y's aren't the same, right? So I can't use y in both those places. I could call one of them y1 and y2, I suppose, but
X squared.
there we go. We did this when we were doing those Shanghai problems. This would be what? X to the 1/3. This point right here would be the point x comma x to the 1/3. Now they have the same x coordinate, so it's okay to reuse x there. But then here the x coordinate, the y coordinate would be x squared, right? That'd be the generic for all the different y values on these curves. That's what they would be. Okay, so what we want to do is we want to take this y value, subtract this y value. Does that make sense? Does it matter what order we subtract them? What if I took this y value minus this y value? We want it to be positive. So does the order matter? How's it going to be positive? You better take the bigger minus the little, right? Well, where's the bigger y values compared to the little y values? The one that's on top, right? So we're going to have to take the top y value minus the bottom y value. Okay, now I've got another little picture that might help you see this. And then we'll have a formula you can put in your notes. But so really what we're talking about is trying to find this, a vertical strip length like this, right? I mean, what we're trying to do, if we go back to my picture here, we're trying to find this red length right here. Okay? Well, how do we find that red length? We find it by taking the top y value minus the bottom y value, right? And so 4 take away 3 would be 1. Now that also works even if your bottom y value is down here in the negative, right? Because you'd have 4 take away negative 3, which would be 7, right? And that is that length, right? So even if one of them's down here and one of them's up here, everything's fine, right? We take the top y value minus the bottom y value. That will give us the length of that strip, okay? And you're going to hear me call that a strip a lot. You're going to hear that term strip because basically what we're trying to do is think about rectangles. Now the width, remember, is the dx. So the top y value is x to the 1/3, right? We got that right there. It says it right here, right there. It says y equals x to the 1/3. So that's what the y value is. And on this one, the y value is x squared. So we take the top y value minus the bottom y value. And notice every single rectangle, every single strip I draw in here, the top y value is going to be x to the 1/3, and the bottom y value is going to be x squared. So there it is, right there. Top minus bottom. Type that into your calculators real quick and see what we get. Now, if we wanted to actually do 5 left rectangles, then we'd have to take 0.2 and plug it into x to the 1/3, which actually you're going to do this on your homework. And you'll take 0.2 and plug it into the x squared, and you'll subtract them and get that height, multiply by the width, which is 0.2, find each of the 5 rectangles, and you'll do it. What'd you get there? 5/12s? 5/12s, which makes sense because this is like a 1 by 1. This is 1 by 1, so that'd be an area of 1, so it's clearly less than 1. So 5/12 is our area. Now, we've already talked about this a little bit, because some of you are probably going, well, yeah, we already knew that. All we had to do is we could have done this yellow area and subtract this red area in here, right? Didn't we already kind of talk about that? And that would leave us the blue area. So, yeah, that's true. But, as we found out, oh, shoot. Oh, dang it. I lost my numbers here. That doesn't work on this one, right? So this one we're going to do here in a little bit, this red area right here, right? We found out that that's not going to work very well to just do like a break it into 2 and subtract them. That's not going to work very well. So we're going to have to come back to that to figure out how to make that happen. Okay? All right. So there's those rectangles I was talking about. All right. So this you might put in your notes, this first thing right up here, this first one here. So to do the area between two curves, it's essentially the integral where we do the top curve minus the bottom curve. Now when I say the top curve minus the bottom curve, what I mean is the top y value minus the bottom y value. But the y value is the function. The y is the f of x, or the g of x, right? So we're going to have two different functions, and we're going to do the area between them. And so we're going to subtract the functions, because what that does is by subtracting the functions, you're subtracting their y values. Right? Because that's what f of x is the output. It's the y value. That's what g of x is. It's the y value. Okay? So when we subtract those, what we're finding is the length of that strip, if you will. Then the delta x is the width of the strip. The dx is the width of the strip. Length times width gives you area of the strip. And then the integral is like the sigma that adds them all together. And that's how we come up with the area. And what we've decided is where the x-axis is makes no bearing on that at all. And as long as we do top minus bottom, we'll always get a positive. That's why we do top minus bottom. Okay? All right, now, that bottom section, what's that all about? What have I got that written down there for? Well, let's take a look at a different scenario now. Let me see what I have. Okay, I'm going to look at that same exact picture here that we had a minute ago. So we're looking for this red area. Okay, and we know that's the 0.11 there. But is there another way we could look at that? Now, why in the world would we want to? Well, it's because there's going to be some problems where what we just did is not going to work very well. So we just did a situation here where, well, let me redraw. So what we just got done doing is we said, okay, here's this red area. Let me rewrite this real quick. And what we said is if I take a strip instead of a rectangle, because what we want is an infinite number of rectangles. So if you do an infinite number of rectangles, they're going to be really skinny. Right? So let's just take a vertical strip here, and imagine we had a whole bunch of these vertical strips in here, right? And the integral is going to add all those up. Well, this strip, the y value, we said this generic point would be x and x to the 1/3, and the generic point on this curve would be x and then x squared. And so it'd be the top y value, x to the 1/3, minus the bottom y value, which is that. And then you don't need parentheses, but I'll just show it. And then 0 to 1. Let's talk about the 0 to 1 a little bit. The way I usually see that is I think, okay, the strips are going to fill the space. We're going to add up the strips that start here at 0, and they go all the way to 1. Okay? And so that's what we're doing. So that's how we got that. We got 5/12. All right. But would it be possible to look at that same situation and think of a series of horizontal strips or horizontal rectangles laying in there? Sure. If I had a whole bunch of horizontal strips and I added up their areas, wouldn't that also give me that same area? Sure it would. Now, why would you want to do that? Well, because there are going to be some problems where we cannot do it with vertical strips, or it'll just be easier if we try it with these horizontal strips. Okay? So that's why it's worth investigating. Now, how would we do the area of imagine this is a little rectangle here. How would we do the area of that? Well, first of all, what would be the width of a horizontal strip? What's that? No. I'm sorry. We're confusing length and width. I'm talking about not this part, but that part. What would you call that? What would we call it in this one? The width of this was the x, the delta x, the change in x, right? What would be wouldn't it be delta y? It would be the change in y, right? In other words, we'd be dividing this way. So it would be delta y, or so when we set up our integral, that's actually going to be dy. So when we have horizontal strips, we're going to be in terms of y, because the width is going to be delta y. Now, what Ali said is, yeah, what's the length? You see why I'm not going to call it height now, because it's laying on its side, so height seems weird. But you call it height, whatever. But the length of this strip will be this x-coordinate. Let me show you it here. Maybe it's easier. To find this length right here, we take this x-coordinate, like 10, and we subtract this x-coordinate, like 7. 10 take away 7 is 3. And that would also work if this was over here this direction, right? If this was negative 2. We'd still have 10 take away negative 2, which would be 12, which is what that length is. So, what order do we want to subtract these? We want to go right minus left. The bigger one is on the right, the littler one's on the left. We want them to be positive, so we take right minus left. But it's the x-coordinates this time that we're wanting to do. So what is this generic x-coordinate here? Now I'll start it the same way we did before. I could call that one xy and I could call that one xy. But there's a problem. I can't really call them both xy because they're different. But I could keep the y's, right? Because aren't they the same y? They're the same y because it's a horizontal strip. So it's the x that I got to get rid of. Okay, so I can't put an x there. No, not cube root of y. It would be, yes. In other words, what we need to do is we need to solve this for x. In other words, this cube root of y, or this cube root of x graph is the same. If you solve for x, let's cube both sides. Aren't those two the same thing? Those two are the same thing. So this x-coordinate, I got to get on the right graph here. This one right here, the x-coordinate is y cubed, isn't it? And this x-coordinate, oh, now this is interesting. We got a square root. That means plus or minus. Why is there a plus or minus? This one over here is positive. What about this one over here? That would be the negative. So the right half, the x-coordinate is the positive square root of y, and over here would be the negative square root of y. So this one is the positive square root of y. You see what we did? We just did the same thing that we did with the other one, except it's the y-coordinates that are the same. The x then, so in other words, what we have to do with our equations, we have to get them x equals. We have to get them x equals instead of y equals. Okay? So now what are we going to do? We're going to take the right x-coordinate, which would be that, minus the left x-coordinate, which would be y cubed. Now, I think once you start getting the hang of this, you're not going to have to write down these generic x and y coordinates. I think it's helpful in the beginning, but I think eventually you'll just see, oh, I just got to solve this for x, and then just, those are my x coordinates, right? It says it right here, x equals square root of y. Right here it says x equals y cubed, right? So that's what the x is on that graph. All right, and then, oh, now what about these numbers? The strips fill the space from down here to up here. Those are the strips we're adding up. Well, that's from what? Oh, that's coincidence there, right? Just because we got 0, 0, and 1, 1. Normally it would not be the same, right? 0 to 1. Before we were going this way, 0 to 1. Now we're going this way, 0 to 1. Okay, type that in your calculator. We better get 5/12. Right? We better get 5/12. But it looks different. If you look at it, it is a different equation than what we had here. Okay? It's a different equation, but it gives us the same result. Okay? And it makes sense that it would. One way we were adding up a bunch of vertical strips to get the area. This way we added up a bunch of horizontal strips to get the area. This is one of those one of those problems that you could choose to do either way. You would probably choose to do vertical. We're used to doing vertical. We're used to using things in terms of x. So if you have a choice, vertical is probably the way to go. Some problems, though, may be easier to do one way or the other. Okay? All right. So back to those notes that we had. So that's where this one comes from down here. Okay? The other way to do it is with horizontal strips. When you do horizontal strips, you're going to have it in terms of y. So it'll be a dy at the end, because the width of a horizontal strip is delta y, change in y, and then right curve minus left curve. Now notice I wrote f of y and g of y. Well, that shouldn't confuse you. We know that f of x means y. We've known that ever since we learned about functions. When you see f of x, you think output, you think y. See g of x, you think y, the y coordinate. Well, same thing here. If you see f of y, you should think x. It's the x coordinate. At g of y, that means you're plugging a y in, and what do you get out? You get out the x. So it's kind of switched around. Okay? So we either do top minus bottom if it's vertical strips, or we do right minus left if it's horizontal strips. Now this is going to come into play in some other stuff we do also. So this concept of top minus bottom, right minus left, vertical, horizontal strips can be very important. All right, let's go back to this problem in sample 3. Okay, let's take a look at what we have here. We said this was the point 7/2 and 1/4. We said this was the point 1/2 and negative 2 3/4. Of course, we have the point 2,1 right there. Now, we found all that in parts A and B is when we found those points. And then you had to write the equation of this line. What was the equation of this line? Y equals what? Somebody got that? X minus 13/4, I believe, is correct. Because once you find A and B, you can find the slope easy enough because you did that with the derivative. You should have had to do that in the first parts here. The slope is 1. So there's the equation of line T. And then we have the equation of these other parabolas. This parabola is y equals x minus 3 quantity squared. And this parabola is y equals x squared minus 3. Okay, so there's our different equations. All right, so because we got 3 of them, we got a line, we got 2 parabolas. All right, so now, based on what we've learned so far, how do we find region R? Now, it's not quite as straightforward as the one we just did. We'll have to do something. Why?
There's the line in there. It's not just between two curves. It's between two curves and a line.
Right. And let's count the line as a curve. I mean, when we say 2 curves, we can call the line a curve. You know what I mean? So what when you say do 2 of them, and I agree, it is 2 of them, but I'm not sure we're on the same page on what 2. Where do you see the 2 of them? So, in other words, if I took, and let me do this in black, if I took and drew a line straight down through here, you're saying do this separate from this? Yeah. That's what I'm seeing. That's what I'm saying. So let's take the left side of this. Now, so why do we need to do that? Why do we need to split it there? Well, there's something, I didn't say this earlier. Let's go back and look. Whoops. Let's go back and look at this picture right here. What can you tell me about every one of those vertical strips? The top of every one of these blue strips hits what curve? X to the 1/3. The bottom of every one of these strips hits the x squared, right? That has to happen for this to work. For this to work, you need the length of every strip throughout the region. And so every strip has to have the same top and same bottom curve. So in this problem, if I start drawing vertical strips, let's do this in blue. Those are all good, right? Those all hit this parabola on top, and they hit the line on the bottom, right? But once you get to the point 2, then what happens to those strips? Now they're hitting the other parabola on top. But they're still hitting the line on the bottom, right? But so it's a different situation. So we have to split this into 2 pieces. We do. Okay, so sometimes we'll get lucky and we'll be able to draw our strips in, okay, whether they're horizontal or they're vertical strips, we'll be able to draw our strips in, and all the way through the region, they'll hit the same curve on top and the same curve on the bottom, and then you'll be fine. Okay, but if they don't, then you have to find where that switches, and then you have to split it apart. Okay, so let's do the blue integral. So the blue area is going to be, remember, what the integral is doing is like a sigma. The integral is adding up all the strips, right? So that's why we do an integral. Okay, now this integral is going to go from where to where? 1/2 to 2. We're looking at the x values here, right? Because these strips are going to fill the space from 1/2 on the left edge, and they're going to fill the space until we get to 2. So 1/2 to 2. And then and the dx is the width of the strip, right? Every one of these strips is a delta x width, dx. So all that's left is for us to do the length of the strip. Well, what's the length of the strip? It's the top y value, right, minus the bottom y value. Well, what's the top y value? Right there. Now, you could put in the generic point if you want. You could say, well, that's the point x and x squared minus 3. You could write that in, right? But you don't have to. You can just say, just ask yourself, what's the y value of this parabola? Oh, it says it right there. The y value of this parabola is y equals x squared minus 3. So we got x squared minus 3. So that's the top y value. Minus, what's the bottom y value? Oh, there it is right there. It's the line. What's the equation of the line? Right here. What's the y value of the line? Oh, it says it right here. Y equals x minus 13/4. So we have x. Now we got to make sure we get parentheses in here. Here's where some of you are going to screw this up. You're going to do everything great, but then you're going to do minus, and you're going to forget parentheses around that. And that's going to make a difference. Okay, type that into your calculator. Oh, forget it. Forget it. What do the directions say? Set up, but do not evaluate. Now, you can look at that one of 2 ways. If you're a positive thinking person, you'd be mad when they tell you to do that. Right? Why? Why would you be mad that they said don't evaluate? Because it's easy points. All you got to do, once you get it set up, all you got to do is type in the calculator, write down the answer. Those are easy points. Now, if you're more negative about it, you'd say, well, I'm glad they're not, because if I screw up the integral, I'll lose those points and I'll lose the answer points too. This is a calculator. Oh, well, this isn't too bad. We could do an antiderivative on this, right? This would be, so, well, there you go. That's another reason. The main reason they do this usually is they put it in the no calculator section. And then you get it set up, and then after that, it'd be like, oh, that'd be a mess to do. We won't mess with it. Sometimes they do it even on the calculator section, though. because it's like, okay, we don't really care if you know how to type it into a calculator. We can teach anybody to do that. We care if you know how to set it up. Okay, so that's another reason they do it. Okay, so let's do the yellow section, be the integral from 2 to 7 halves, and that these fill the space from 2 to 7 halves, and then be the top parabola, which is x minus 3 squared, be the top y value, minus the bottom y value, which is a line, x minus 13/4. And then your dx. Don't forget the dx. It's not, you're not going to get counted off probably if you do. But and then you would add those two answers together, right? So you take that, and you would add those two together. Okay? So this is how we do area between two curves. All right? Now we should practice one, I think, with a horizontal strip situation. So let's take a look at one. I've got one here on a PowerPoint, except I hate to do the whole PowerPoint right now because then my video goes away. My video quits. So let's go through here, and I'll just go through the. Okay, here would be one right here. Let's take a look at this scenario right here. So here's a region. We got square root of x, right, like this. And we got the line y equals x minus 2. So if I was to graph this, let's, okay, let me take, let's go over here and let's do this one. Okay, so if I was going to take this region right here, and here's square root of x, so it goes like that. And here's y equals x minus 2, which comes down something like this, okay? So I've got this region in green that I'm trying to find, okay? Now, this is y equals square root of x here, and this line is y equals x minus 2. All right, so one way to do it, let's say, so one of the things you're going to notice, I'm going to show you here in a minute, is you got to decide, am I going to use vertical strips or horizontal strips? Sometimes you have a choice, like the problem we did it both ways. And on your homework, you are going to do some both ways. Like a couple problems, I'll say do it with vertical strips, and then the next two problems, I say now do those same problems, but with horizontal strips. So we're going to practice doing both, okay? How would you do this with vertical strips? You'd have to break it up. Where? Right here, I think this is the 0.20 right here, and this is a 0.42, I believe. So that's something else. I've kind of glossed over that, but you've got to be able to find these intersection points, right? Now your calculator comes in real handy there. Just set those two equal to each other, right? Just set this equal to this and find those solutions of where they cross, right? Or you can go on your graph screen of your calculator and you use intersection. You can find where they intersect, okay? So you have to do that. And sometimes they won't come out nice. Sometimes they'll be decimals, and you'll have to carry those out to 5 or 6 decimal places, okay? But these are pretty nice. So in this case, so if we were doing vertical strips, we have to split it right here. These strips, so let's just set that up. So the first integral would be from what to what? 0 to 2. The top y value is root x, right? Says it right there, y equals, minus the bottom y value, which is 0. That's just a regular old area, isn't it? But I'll be honest, even now, once we learn this, I almost think of this as my second curve. I just think of the x-axis as my second curve, and I do top minus bottom, okay? So, and then our dx right here. And then plus, now let's do the second integral here. So the second one, now my y values are hitting the line on the bottom. So the top y value is root x minus the bottom y value, got to put that in parentheses, x minus 2. And that goes from 2 to 4. So that's how we would have to do the red area, that area using vertical strips. But what if we were going to do horizontal strips? Wouldn't we only need one here? Because every horizontal strip that you draw is going to hit the line on the right, and it's going to hit the parabola on the left. So you can do it with just one. So the integral would be from, careful, 0 to 2. The strips fill the space from a y value down here of 0, and they go all the way up here to 2. So you got to use the y value. It's going to be a dy here, right? And it's going to be the right x value. What's the right x value of the line? You would have to add 2 to both sides, and you would have to solve for x. Because think about what I just said. What's this x value? Oh, it says it right there. X equals y plus 2. So the x value of the line is y plus 2. So we would take y plus 2 minus, what's the x value of this? We'd have to solve for x, and we get x equals y squared. So the x value of the parabola is y squared. So we would have that right there. So there you go. So you could do it in the red. Type that in your calculator, you'll get an answer. Do it with horizontal strips, type that in your calculator, you'll get the same answer because it's the same region. So horizontal strips preferable there, so once you get the hang of this, it's pretty easy to make horizontal strips if you want, or you can divide it into 2 pieces and do that. Okay? All right, and let's see what else. Seems like there was something else here. Okay, this is a region. This is going to be a picture for part of your homework, so I'll leave that up here. All right, so on that homework sheet that you all picked up, so we're going to go ahead and work on that now. Now, the first 2 problems, okay, so let me just talk through this real quick. The first 2 problems have you sketch a region and then add up these rectangles. So you actually have to go, okay, they find where they intersect. In this case, 0 to 1. If you're going to do 5 left rectangles, they'd each be 1/5 wide. So you'd actually have to take 1/5 and 2/5 and 3/5 and 4/5. You have to plug into the top curve, plug into the bottom curve, get those y values, subtract them. You actually have to do those calculations because it's less than 10, right? So if it's 5 of them, so you're actually going to calculate that, and then you'll calculate the actual area doing this top minus bottom we talked about. Okay, so that's 1 and 2. 3, you're going to use. This is one of the pictures. It's in your book. They tell you it's one of the examples back in the section. I went ahead and drew it up here for you too. So they're going to have you do this with vertical strips. Now, what would be the better one? Vertical or horizontal? Horizontal would be great because you'd hit the line on the right and you'd hit the parabola on the left. That would definitely be the way to do it. But in problem number 3, it's like 4 parts. Well, they're going to lead you through doing it with vertical strips. So one part you would do this part, one part you do this down here, another part you do, well, I don't know, it's almost a triangle the rest of the way, I don't know. So they lead you through doing this, breaking it up into pieces and doing it with vertical strips, which is good practice. We need to do that. So that's what number 3 is. Number 10 isn't related to any of this stuff. Number 10 is a problem about units. It's kind of like that gallons per year we did. It talks about here's an integral, here's what its units are, explain what this integral would mean. So it's just good practice at thinking about what we've been talking about with those story problems. Okay? Then 17 and 23 give you 2 equations and tell you to graph it and find the area of the region using vertical strips. So 17 and 23, you have to use vertical strips. Then on 29 and 35, that's those same 2 problems, but using horizontal strips this time. Okay? All right. Rest of the time's yours to work on it.